Having learnt about the basics of OFDM, now we start looking at the bigger picture and try to figure out what the LTE downlink frame structure looks like. And we return to our familiar space frequency time domain, where we have time in the x-axis and frequency on the y-axis. We kind of looked at our basic building block, which is this two resource blocks in the time frequency domain, and which are called subframe, which is 1 millisecond long, and we said there were 12 subcarriers over here, so 180 kilohertz. And this is our basic building block. This is going to be our basic Lego piece, which we will go ahead and replicate it. So if we have a frequency domain, if we have something in the order of 1.4 megahertz, which is the bare minimum that you can have, you end up having 6 of these 180 kilohertz resource blocks in the frequency domain. If you look at it, this number, if you multiply 180 by 6, you will get a number which is 1.08 megahertz. So the frequency 1.4 is greater than the 1.08 megahertz, and there are some guard bands at the two ends of the frequencies. Well, we are going to focus primarily on these basic 6 resource blocks that we have. And if we take these 6 resource blocks in the frequency domain and we kind of replicate them in the time domain, we end up with something which is called a radio frame, which is 10 milliseconds long. And this radio frame will repeat itself forever, once after the next, in the time domain, and we essentially get our LTE downlink frame coming to us for eternity. Each of these radio frames has a system frame number, or so SFN. So this is a system frame number N, and the next one will become system frame number N plus 1. Obviously there is a modulo operation that happens somewhere where the system frame number comes back down to 0. And these radio frames are the main bigger building block. So if this subframe is the smallest building block, these radio frames are on the macro size of a building blocks that are replicated one after the other. Just to keep in mind that the way the numbering is done of the subframes within a radio frame is that the very first subframe in a radio frame is 0, 1, 2, all the way you will end up with number 9 subframe over here. Now if you've got a little wider bandwidth, let's assume that you've got a bandwidth which is 3 megahertz wide, you end up with 15 of these resource blocks in the frequency domain, and they end up, if you look at it, it ends up taking less than the overall 3 megahertz, and this is like 2.7 megahertz. So on, if you've got 5 megahertz, you've got 25 resource blocks, so you'll have 25. And if you've got 20 megahertz, you've got 100 resource blocks in the frequency domain. So hundreds of these resource blocks going up and down, and the same pattern kind of being repeated in the time domain. So you get this kind of ugly looking bathroom tile structure, right? If you kind of remember seeing some of these bathroom tiles, they have got this kind of a color, and then they go on. Obviously this coloring is just a representation. One thing you'll notice is that these numbers, if you've got 100 of these, you would have expected 18 megahertz, but then you have this 15 megahertz, 15 kilohertz kind of additional, and this is your 15 kilohertz, which is at the center of the band, which is at the DC frequency. So this is called the DC subcarrier, and there is no information carried in this subcarrier, which is when you kind of will bring it down into the baseband. This is at the 0 frequency. So 0 frequency is essentially no signal being sent in this subcarrier. So all of these are kind of padded by 15 kilohertz, and that's why you get these numbers which are not very round numbers. Now, having looked at this downlink radio frame, the main idea is when a mobile starts looking at these downlink radio frames, he's got very little idea of where exactly the center frequency is, how many of these resource frames are there. So the mobile comes in and starts looking at these radio frames, and he's seeing this kind of a frequency structure, time frequency structure going by. So he's somewhere here in time, and he sees that these kind of this kind of a math structure and frequency domain, and he's got some idea that somewhere in here is the center frequency, but where exactly is the center frequency, he doesn't know. So in this slide we will look at how the mobile kind of synchronizes to a downlink radio frame. So the very first thing that is provided to help the mobile to synchronize to the downlink radio frame are what's called these primary synchronization signal. And these primary synchronization signals are in the middle 62 subcarriers. So 62 subcarriers are the ones that are carrying the primary synchronization signal, and these are repeated every 5 milliseconds. So you have every 5 milliseconds the mobile is kind of starts seeing this structure. So this is the very first thing the mobile is able to decode in the downlink channel, and this is centered right at the middle of the center DC frequency which is going to be there. There are 5 resource elements which have got no energy in it, so that's why they are shown in black. So there are 5 resource elements on the top and 5 at the bottom, and this makes up 72 carriers. So if you look at 72 divided by 12, you see that these are actually 6 resource blocks, and 6 resource blocks are the minimum that gets transmitted in LTE in a bandwidth of 1.4 megahertz. If LTE's downlink is 1.4 megahertz, you get this. So this structure of your primary synchronization signal is the same irrespective of your overall bandwidth. So even if your bandwidth is 20 megahertz, you will have this kind of a structure of the primary synchronization signal. So with this primary synchronization signal, the mobile kind of knows that, okay, it's gotten a structure of 5 milliseconds, and the mobile also knows that this is sent in the 0th subframe, and then again in the 1, 2, 3, 4 in the 0th and the 5th subframe of every radio frame, but he has no idea whether this is 0 or this is 5, or it's actually 0 is this one and 5 is the next one. So how does the mobile find out which is the radio frame structure, where is the 10 millisecond boundary? Is this the 10 millisecond boundary, or in fact the 10 millisecond boundary is this one? So in order to help the mobile to figure out the 10 milliseconds boundary, there is the secondary synchronization signal, the SSS, and that is transmitted right in the previous OFDM symbol compared to the primary synchronization signal. The interesting thing is that these secondary synchronization signals have 2 different patterns, and one of this, which we are shown with the solid filled in orange, and the other with the shaded one, give the mobile the exact indication of the 10 millisecond radio frame pattern that was not visible with the primary synchronization signal. So with the secondary synchronization signal, the mobile now knows that the radio frame structure is actually starting from here, then ending here, and the next one goes on from here. The other important information that actually is provided in the primary and the secondary synchronization signal is something called the physical layer cell identity, or it's also called PCI. You will kind of see this in the standards as being called PCI, the physical layer cell identity. So this is like each cell, each base station has an identity, and the identity of the base station is actually a pretty long number. I think it's a 48-bit number, but 48 bits is a lot of value to kind of try to put in and put it and try to provide that for a cell. For a mobile to find out there is a short identity which is used for the cell also, which is called this physical cell identity. It's like saying that, okay, the actual name of the cell is Ibn al-Walid al-Khalid al-Wahid. You're like, oh man, I can't remember that name. So you go ahead and say, okay, just call me Al. And so this is actually the Al name given to the cell. The way the physical cell identities turn out is that your PSS gives you one of three values for your cell in part of your cell identity. So from your PSI you figure out either your group's physical cell identity group is 0, 1 or 2, and then from your SSS it gives out which of your identity is present in 158 of these of the values that can be taken. So your SSS gives you a number, for example, that if this number comes out to be 45 and this is 0, 1, 2, you exactly know that your physical cell identity is this particular value. If you take 158 multiplied by 3, you will figure out that there are a total of 504 physical layer cell identities, your PSI. So by decoding the primary synchronization signal and your secondary synchronization signal, the mobile knows the physical cell identity of the cell. The mobile doesn't need to decode anything else to find out this shorthand identity of the cell, and this is important and used in a lot of measurements when the mobile is trying to figure out which other cells am I able to hear in this vicinity. It can just make the measure, it can just decode the PSS and the SSS and find out what the identity is and provide measurement reports based on these physical cell identities, and not have to read and get the overall cell ID, the real full name of this cell. All right. So with the primary synchronization signal and the secondary synchronization signal, we've gotten the main radio frame structure, and once the UE has figured out the PCI of the cell, it is able to find out there are some reference signals that are transmitted in each and every of these subframes. And once it knows the PCI, the mobile is able to find out where exactly these cell reference signals are. And these cell reference signals enable the mobile to actually find out the exact frequency and time structure and be able to kind of lock on to the right frequencies and know and get its oscillator to kind of to be fairly accurate. And these cell reference signals are actually all over in each and every of these subframes that we are seeing. There are 8 of it in each subframe that is transmitted. So you have 8 cell reference CRS in each of the subframes, and this enables this grid provides the UE to be able to synchronize to the frequency in this entire 3 megahertz that we are seeing. In addition to this, what is being the next thing that the mobile goes ahead and decodes is actually the broadcast, the physical broadcast channel, and this is kind of the most important and basic information about the cell that is being broadcast, and it is broadcast every 10 milliseconds. So the physical broadcast channel is sent every 10 milliseconds, and actually the information in this physical broadcast channel changes can change every 40 milliseconds. So whenever SFN mod 4 is equal to 0, you have there can be some new information in the physical broadcast channel. What is carried in this physical broadcast channel is something called the master information block. So master info block, which is also called MIB. Now what exactly does the MIB have in it is that the MIB kind of tells the mobile what is the downlink bandwidth. So is it actually 3 megahertz or have I gotten 20 megahertz that is being allocated? It provides the system frame number, so it tells what exactly what is the system frame number for this radio frame, and it also provides some configuration of logical channel, which we will not go into too much detail, which is called the physical hybrid ARQ. So ARQ stands for automatic repeat request. And it gives some information about where a certain information for the physical hybrid ARQ channel is, and once the UE is able to decode the physical broadcast channel, it is able to then decode some more information about the cell, which are there in some secondary information blocks, about which we'll go into some more details a little bit later. But we first look at what the downlink physical channels look like, and this is these are essentially the key channels or the key information that gets transmitted in the physical layer of LTE. We had obviously come to the very first downlink physical channel, which is the physical broadcast channel, which is carrying the MIB, as I said, and that is present in the 0th subframe of every radio frame, and it is actually 4 OFDM symbol wide. So it's 4 FDM symbol wides and 72 subcarriers are present in there. In addition to this physical broadcast channel, the other key channel that is available in the physical layer in the downlink is called the physical downlink control channel. And in the first 3 OFDM symbols of every subframe, of every 1 millisecond subframe, are present these physical downlink channel elements, and this is the most important control information that provides a map of what information is present in the remaining part of these these subframes. And what is in the remaining blue parts of the subframe is called the PDSCH, or the physical downlink shared channel. So this blue part is the PDSCH, which contains all the information that the mobile needs from the network, and the PD physical downlink control channel, PDCCH, is actually a map that tells the mobile where the information, a pointer to where the information is, and for whom this information is destined for. So the two key downlink physical channels that we will be looking at are actually the physical downlink control channel, this red one, and the physical downlink shared channel, the blue part of it. In addition to these two channels, there are some other control channels that are also present. There is something called the physical control format indicator, and that is present in the very first symbol of every subframe. It's got a few network elements, and as I just said, that this PD, the physical downlink control channel, is 3 OFDM symbols wide. It's not always 3 OFDM symbols wide. It can be either 1, 2, or 3, and the physical control format information actually tells the mobile whether the physical downlink control channel is 1 OFDM symbol wide or 2 or 3. So it's an important bit of information that is kind of carried. It's carried in the very first OFDM symbol and in some specific places in the very first OFDM symbol of every subframe that will be there. In addition, as we had kind of said, we had looked at the MIB had provided some information about this physical hybrid ARQ indicator channel, and we will not be going too much details into the physical layer, so we don't have to kind of bother about what exact information it provides. But that again is in the very first symbol of the OFDM in specific places that the mobile knows it should go ahead and read. So these are our main physical channels that are present, and this is the main important kind of structure that our downlink channel has, that the mobile kind of looks. That's this red and blue tile structure. Suddenly it's starting to look a little bit more interesting than the here it is in multicolor, which is nice and good. Here these various colors are essentially saying that this information is for UE number 1 and this information is for UE number 2. So there are different colors for different mobiles, and we get this nice multicolored tile structure which looks beautiful. And this is what your downlink physical channel will look like in multicolor if you give it this kind of a representation. So this is just for fun. I thought I would create something and share this with you.